So let me start with the topic of photoelectric emission. Actually, why I have choose this topic? The thing is, while observing or while analyzing the PYQs of JEE mains, I observed that from this topic there were certain question asked. Fine, and also this topic will form the base for the chapter dual nature of matter and radiation. So in order to understand that chapter better, we need to make this topic very clear. Also from this topic, Einstein's photoelectric emission was the most important part, and while observing, as I have told you, I saw many questions asked there. Okay, so without wasting any time, let me start. And before starting, this will be my topic of discussion, or this is my table of content. That is, first we'll be studying the photoelectric effect basic, then some important term, then we will go with the we can say Einstein's equation. The next will be your factor affecting photoelectric, and at the very end we will be solving an illustrative example of JEE mains PYQ. I hope it's clear to you. Okay, next what we'll do, let's start. Before starting the main topic, did you ever observed or did you ever had a curiosity like how does a solar PV cell work? Actually, there's a very curiosity rising question, that how can we like use the solar light, how can we just use the solar light to how can we use solar light to generate electricity? Actually, solar PV cell and etc type of electricity are one of the most we can say rapidly growing form of electricity generation in our present time. Fine. Now as we can see, there were there are many cars, there are many vehicles who have opted for this solar type of energy generation. Also in many household, we can observe nowadays in many household they have installed that solar proof roof, that is a solar PV cell roof, so that they can get electricity in a very cheap rate. Fine. So these are the we can say these are the very much advantage of this photoelectric emission process. Fine. So stating that, let us start. Okay, the first part which we'll be going to is going to teach you is the brief history of photoelectric emission. Okay, now see, this effect was first observed by the German physicist called Hertz. Fine. What he actually observed, he observed that when he illuminated a metallic surface, suppose say this is my metallic surface, okay, this is my metal, this is my metallic surface. So when he illuminated this metallic surface with a UV light, we can say this is a UV light. Okay, he observed that there was certain form of we can say current generation. It's quite obvious, you won't see those photoelectrons, but he observed that there was some sort of electron flow, there was some sort of charge flow. Fine. So he observed that actually when he illuminated the UV light on two metallic electrode with a voltage applied across them, he observed some sort of sparking going on. Okay, so this is the experimental setup which he actually used in his experiment. This is my experimental setup. From this experimental setup, let me explain this experimental setup to you, it will be very much clear to you. Fine. Okay, now in this experimental setup, what he had done, actually this is this evacuated glass. Fine. In this evacuated glass there are two metallic contacts, one is called cathode, let me name it as cathode, and another, as you can see, is the anode. These are my two metallic contacts, and anode initially is kept in a positive potential as compared to this cathode. Fine. Okay, this is my quartz glass, and through this quartz glass my light will enter this setup. Okay, and this is the sun. As we know, sun is the universal source of all frequencies. So from this sun, this UV light will go to this cathode through this we can say aperture. Fine. Okay, and this is a DT switch, that is we can say this is a commutator type switch. Okay, and this is that ammeter, basically its range is of micro level. Fine. And this is a voltage measuring device, and this is the battery setup and all. Okay, our important part is to see this part. Okay, this part, as you can see, this is the cathode, this is the anode. Okay, now what will happen when UV light will strike this cathode? There will be a generation of photoelectrons, there will be generation of some electrons. Suppose this is the generation of electron, like from there it got pumped up like this. Okay, and also there will be many electrons. It's not like there will be one single electron, there will be many electrons, and these electrons, since electron have a negative charge and anode have a positive charge, so it will be attracted by this anodic potential and anodic positive potential. Like this, these electrons will get attracted by this anodic positive potential. Fine. So this was all his setup and all. Okay, actually he studied, or he measured this one, we can say he measured this one, this photocurrent, via this we can say micro micro level emitter. This is the micro emitter connected in series. Fine. Okay, this was all his experimental setup. Now the thing is, one of the most important, we can say, feature of this photoelectric emission is that it explained it, we can say it greatly explained the particle nature, we can say the particle nature of light, and it was the main testament to the particle nature of light. Remember, as we know, initially in initial phases people used to think that light was made up of wave, but this photoelectric emission proved that light is made up of tiny particles. Okay, and we call it as photons, and these photons have a energy. Okay, this photon have a particular frequency, particular, we can say, wavelength. Fine. Okay, so this was all his setup of Hertz. Now we have accomplished the first point, this is the brief history. Now we'll be studying the photoelectric effect. What is the actual photoelectric effect? Okay, now photoelectric effect, if we study, then what I have written, it is the phenomena, or it is the, we can say, physical phenomena in which a beam of sufficient frequency. What does this sufficient frequency mean? This sufficient frequency basically mean that the frequency of incident photon should be more than, we can say, the work function frequency, or we can say the threshold frequency, f cutoff, or threshold or cutoff. Fine. So this sufficient frequency basically mean that the frequency of incoming or frequency of incident photon should be more than this cutoff. Okay. So what I have written, phenomena in which beam of sufficient frequency fall on metallic surface and electrons are ejected from metal. Let us consider this, we can say, setup. This setup is almost similar to that Hertz one. I have just modified for your, we can say, convenience. Okay, in this setup, as you can see, the similar case, there will be radiation, there will be a particular radiation incoming, there will be a particular radiation incoming. Fine. And upon striking this metallic surface, it will eject photoelectrons. Like this. These photoelectrons, under the influence of this anodic positive potential, will move like this, and upon moving, this photoelectron will be captured by this, and that captured photoelectron at anodic plate will be sent through this wire. This wire will gain this electron, and hence this bulb will glow. Like this. Okay. So in general, or we can say in a summary form, what we can say about photoelectric effect is the ejection of photoelectron from a metallic surface upon the application of light. Fine. And how we can measure the photocurrent? We can measure by using this micro level emitter connected in series. So our second checkbox is also done. Our third topic is to explain the important terms regarding this. Okay, the first important term what I have wrote is about the photoelectron. So can you just tell me, like, what we mean by photoelectron, or like why we say the electrons as photoelectron? Yeah, you are absolutely correct. The reason is those electrons, since those electrons are ejected after the application of photons, or since those electrons are ejected under the influence of photon, hence we name those electrons as electron ejected from metal surface. Okay, like electron ejected from metal surface under the influence of this photon. Fine. Number two, what I am going to teach you is photocurrent. It's quite simple. What does photocurrent means? In simple term, what we mean by current means, we can say flow of charge per unit time. Flow of charge per unit time. Similarly, the case of photocurrent, in this photocurrent, the flow of charge will be associated with the photoelectron, and per unit time, it's quite simple. Fine. Okay, number three is that we will be studying about the threshold frequency. Now, what does threshold frequency mean? As I have explained it, that we need to make incident light at a sufficient frequency. There is the sufficient frequency. Now the sufficient frequency, I have explained this. Okay, here now we'll be understanding this threshold frequency in detail. The threshold frequency is basically the minimum frequency required for ejection of electron from metallic surface. As I have said you earlier, that is, the threshold frequency is the minimum frequency above which a metallic surface should be struck by a light so that it eject photoelectrons. Fine. So it is the minimum frequency. Required. Fine. The next we are going to start about the threshold wavelength. What do we mean by threshold wavelength? Threshold wavelength is basically the maximum lambda or the maximum wavelength required for photo ejection. There you might get a confusion that why I have used a minimum and why here a maximum. Actually, frequency and wavelength hold a inverse relationship. So respecting this relationship, what I can say that if in threshold frequency, it is the minimum frequency required to eject like that photoelectron. So in case of threshold wavelength will be what? It should be the maximum wave, it should be the maximum wavelength, it should be the maximum wavelength of the incoming photon to like to start the process of, we can say, photoelectric emission. Like above it, above this lambda, above this wavelength lambda, there won't be any photo emission. Okay, so this is the maximum case. Okay, so to occur photo emission, what we should do, we should make the metal surface incident by a light having maximum wavelength less than it, or having the maximum wavelength less than the cutoff wavelength. While in frequency it's inverse, the incoming photon should have frequency more than this threshold frequency. Fine. So our another checkbox is done. The next topic which we'll be going to start is the mathematical form of Einstein equation, and this equation is actually the important one. Or from this equation, like basically we can say we can expect question from this one. Fine. So this is the most important one. Now this Einstein equation, like due to this equation only he got his Nobel Prize. Okay, so what was his equation? This, before starting the equation, let us understand what is the work function. So what is the work function? Work function is the minimum, this is the minimum energy required for electron ejection from metallic surface. Okay, so what does this work function mean? This work function means, suppose this is my metallic surface. Okay, and in this metallic surface I have incidents, I have made incident photon. Okay, and photon, this energy is E. So what will happen, this work function you can consider is just like a tax. Okay, like that tax which you have to give to this metal surface, so that you can, this is my metal surface, so that you can take an electron out of this. Okay, so what does this work function basically mean? Work function is a sort of tax which the incoming photon need to give to this metal surface, so that that photon can eject an electron from it. Fine. Okay, so this we mean by work function. So, and this is the equation of Einstein, that is K max equal to h mu minus h mu naught. Now what does this h mu naught means? This h mu naught is basically the work function which I have mentioned here. H mu naught, this is the minimum energy required, and this h mu basically stands for the energy of incident photon. Okay, that is since I have explained here, as you can see, the energy of incident photon is your h mu. Okay, while from this h mu, if we deduct this work function, that is h mu naught, then the rest of the energy will be used as a kinetic energy of the ejected electron. The electron will be ejected, or electron will move by this energy of K max. Fine. So this we mean by K max equal to h mu minus h mu naught, where this K max is the maximum kinetic energy. Mind it, this is the maximum kinetic energy of the ejected photoelectron. Fine. And obviously this work function depend on the metal, it is a metallic property, or it is an inherent metallic property, depend on the metal. Fine. Okay, saying this, it doesn't depend, it neither depend on the incoming photon property, like what is the property of incident photon. It doesn't depend upon the wavelength of photon, neither the frequency. Fine. Okay, see, I have also crafted this for you. That is, suppose say this is the metal surface, this is the metal surface. In that metal surface I have made incident light of h mu. This, from this h mu, it have gained h mu naught, and after gaining the remaining energy K max, it went through this K max. Fine. Okay, our another checkbox is also done, and we are going quite well. Okay, so I hope up to this it's very much crystal clear to you. If you have any question, then you can please ask me, please feel free to ask me. Okay, so let us go with the next part, that is factor on which it depend. It means basically, it means the photocurrent depend. Fine. Photocurrent depend. Okay, number one which I have marked is of the light intensity. Now what does intensity mean? Intensity mean, we can say, for in case of light, intensity mean number of photon per unit time and per unit area. So what does intensity in general means? Intensity in general means number of photons per unit time per unit area. Now see, I have I have a theory of my own. I don't know whether this is mentioned in a book or not, but this is my theory. this theory is named as one photon one electron theory. One photon one electron theory means a single photon is eligible, or you can say is eligible to remove a single electron, to eject a single electron. Okay, now the thing is, it can never be possible that a single photon can eject multiple electrons. No, a single photon, a single electron, single photon, a single electron. Fine. So, and also this, as like respecting this one, I can say that if I increase the intensity, then can I observe there is an increase in the light intensity, or like can I observe there is an increase in the photocurrent? Can I observe? Like, can I write it? Just think for once. Yeah, if we increase the intensity, what we can see, if we increase the intensity, then we will be increasing the number of photons. And if we increase the number of photon respecting this one photon one electron, if we increase the number of photon, then there will be a net increase in the electron, as mentioned in this graph. As you can see, in the y-axis I took photocurrent, in the x-axis I have took the intensity. As we are increasing the intensity, you can see the photocurrent is increasing. I hope you are clear. Okay, so this was about the light intensity. Next we'll be going with the light frequency. Yeah, this is also the important one. Light frequency play we can say a varied role. As we know, the energy of photon is directly proportional to the frequency, also inversely proportional to the wavelength. So if we observe from there is, and also this is from Einstein equation, what I have wrote here, K max equal to HF minus HF naught. So what I can observe from here is, if we increase the frequency, we can see that there is a net increase in the kinetic energy of the photo electron ejected. Fine. Now you might ask me, what will be the effect of we can say frequency in photocurrent? I will be taking it in the next part. Okay, that is in the next factor I will be taking it. Please don't worry. Also, one of the important term, you can see this, I have like marked here a f naught value. What does this f naught value means? This f naught value is basically your threshold frequency. Actually, see, before this threshold frequency, the kinetic energy is 0. Before, from there to there, the kinetic energy is 0. Why 0? Because as I have told you that the incident light should have a frequency more than this f naught to cause photo emission. So before this region, like in this region, what's happening, the light won't having that requisite frequency, and hence there will be no photo emission. And if there is no photo emission, it's quite obvious that there will be no velocity, or there will be no kinetic energy. Fine. Okay. And the last factor is the potential between electrode means basically between your we can say cathode and anode, basically the difference between your cathode and anode. Okay, so initially what I have just told you, initially the anode was with positive potential as compared to its cathode counterpart. Fine. So what does this mean, potential between electrode? Like here we will be going to study about a concept of stopping potential. It's quite simple, stopping potential. So what does stopping potential mean? Stopping potential. So what does stopping potential mean? Stopping potential is the minimum negative potential required to stop the most energetic kinetic, or in other words, we can say the most K max electron. This like this potential, this stopping potential is basically, we can say, suppose let me draw the figure. Okay, this was the initial setup. In this initial setup, as you can see, the anode was in the plus state, the cathode was in negative, so there will be ejection of photoelectron. That photoelectron will be attracted by this anode. That's fine. Okay, now if we reverse the direction, on reversing the direction, what we can observe, if we reverse the direction, that is, if we make it like this, this is my anode, this is my cathode, and now this is my plus, this is my minus. So like what will happen, the light will strike this cathode plate, the electron will get ejected, and that electron will move under the influence of its Ke max. But as you can see, important thing, the electron is of negative charge, this plate is also of negative charge, so there will be a mutual repulsion among them, and that is the kinetic energy max will be converted to the potential energy of repulsion. Okay, like under like as you like it's quite a simple sense, as if you can think that electron is also negative charge. I have reversed the potential, that is the anode is also negative charge. So this negative electrode, this negative electron and this negative anode will have a mutual repulsion. So that amount of minimum potential, that amount of minimum potential we need to apply between two plates, so that we can stop or we can halt the movement of the most energetic electron. Okay, so this was about the stopping potential. As you can see, I have marked here that K max is equal to the potential energy repulsion, that is K max equal to Q V naught. This is actually the formula of the potential energy. This is the formula of potential energy, that is like what will be the potential energy stored if we accelerate a charged particle having a charge Q to a potential difference of V naught. So this is my potential energy. Like this is basically a formula. You can you can know it, simple. So the K max will be equal to K V naught. Actually the electron, that is the electron having this K max, when it will stop, just think, this K max, the most energetic photoelectron, when it will stop, it will stop, and like it will stop when all its K max will be converted to its potential energy, this QV naught. Okay, like suppose say this was my electron and it was moving and this is my cathode. Suppose say this is my, like it get ejected from the cathode plate and this is my anodic plate. Okay, this is my negative plate. So like this photoelectron will be moving, and there, like initially it had a great speed, but with time, but due to the repulsive force of this negatively charged anode, it will slowly lose its velocity, and a time will come that it will completely stop here. Okay, now the moment it stop here, and the potential we have applied to make it stop is known as your stopping potential. And also from here, as you can see, this whole K, like in this position the whole K max will be get converted to the potential energy. I hope it's fine. Now the last part of it are the two graphs. In this two graph, what I have done the graph between the photocurrent, anodic potential. This is my we can say stopping potential. This is minus V naught, as I have told you, this is the minimum negative potential. So this is my stopping potential, this is going to be my stopping potential. Fine. Okay, so as you can observe from this graph is, actually in this graph what I have done, like I have made, we can say I have made the frequency constant while I have changed the intensity. Now as I have said, like as I have told you earlier, that intensity directly proportional to the photocurrent. So see, here I have marked three intensities, I3, I2, I1. So can you tell me the order of this intensity? Yeah, please go on, please think for once, and can you please tell me that what will be the order of intensity? I hope you have done it right. The order will be I3 greater than I2 greater than I1, because see, the I3 having the maximum of photocurrent, then then the turn is of I2, and at last is of I1. So this is my we can say this is my arrangement of photocurrent, which will be directly proportional to the intensity I3, I2, I1. Very good. Now see, this is my stopping potential. Okay, this is my stopping potential. Actually see, this was my photocurrent, and there from this part you can see that I have applied negative potential, and from this part you can observe, if we consider this I3, you can observe that like photocurrent is decreasing, and a moment will come, it will completely stop. From there, it is the origin, so it will completely stop here. The potential, the maximum, we can say the not maximum, the minimum retarding potential, which is enough to cause the movement of electron to stop. So this will be my retarding potential, is negatively. Okay, so I guess it's quite clear from the graph. Similarly for I2 also, similarly for I1 also. Now if we see this graph of this photocurrent versus frequency, like as I have told you earlier, this photocurrent versus frequency graph, you can see this graph and this graph is bit different, but like the logic is same. Okay, so in this graph, can you tell me, okay, I have written here, it's like it will be something good for you. I have already written here. You can see that these are my different stopping potential. So what I have just told you, I have told you that if the energy of the photon is more, then we need what? If the energy of the photon is more, energy of the incoming photon is more, then what does this mean? This means there will be a there will be a proportional rise in the K max, and if there is a proportional rise in the K max, what we can infer from it, that there will be a proportional rise in the stopping potential also. That's the important term. Fine. So from this figure you can observe that these are my 3 stopping potential, and corresponding these are my 3 frequencies. So this f3 is the maximum frequency. For maximum frequency we need the, from maximum frequency amongst these 3 we need the maximum stopping potential. It's quite obvious, it's quite a simple sense you can think that from this relation. Fine. Similarly for this frequency f2, similarly the frequency f1. So I hope it's entirely clear to you. Now the last part of this video is going to be the numerical understanding of the topic which I have discussed, that is photoelectric emission. So we have done all the topics which I have we have done all the topics which I have marked earlier. This is the last part. This is a previous year JEE Mains. This is a PYQ from JEE Mains. Okay, this is the previous year question. Let us read the question. What is the question saying? The question is saying that surface of a certain metal is first illuminated with lambda 1 equal to 350 nanometer, this stands for nanometer, and then by lambda 2 540 nanometer. Fine. Maximum speed of photoelectron in 2 cases differ by a factor 2. Fine. Okay, so we need to find the work function is closest to. So this is the question. Let me, I guess the question is clear to you still. I am going to explain this question. In this question what is saying that we have a metal surface, okay, and in this metal surface I have made incident lambda 1. I have made incident a light of we can say wavelength lambda 1 having 350 nanometer value. Fine, 350 nanometer. And in second case, for the same metal only, for second case we have made incident another lambda of value 540 nanometer. Okay, in both cases what we have observed that the we can say this velocity or the speed by which the electron got ejected is differ by a factor 2. That is the, we can say if this is my Ke1, this is my electron, and this is my Ke2 electron, so the velocity of Ke1 is we can say differ by a factor 2 of Ke2. And obviously as you can see the wavelength of this first case is my first case, this is my second case. The wavelength of my first case is less, so obviously in this case the kinetic energy will be more. So what we can write it as Ke will be more than your Ke2. Okay, now let us start with the question part. Fine. So using Einstein's equation basically means Ke max is equal to energy of incident photon minus work function. Okay, we'll be using this, or we'll be applying this for 2 times. For number 1 case what I can write it as Ke max, or Ke max for 1 will be equal to, and energy in terms of wavelength we can write it as hc by lambda. H is the Planck constant, c is the velocity of light, hc by lambda. Lambda 1, that is lambda 1 is your 350 nanometer. Okay, 350, let us convert it into SI 9 minus 5. This is my equation 1. For equation 2, similarly what I can write, just see that we have illuminated the surface with lambda, that is lambda having a value of hc, similarly by 540. See 540 written here, 540 nanometer. I think you are seeing it, 540 into 10 raised to the power minus 9 minus 5. This is my 2 equation. Fine, these are my 2 equation. Okay, now what will we going to do? We'll be just going to solve it. Now see, this part is sorted, we need to sort this part. Okay, now the thing is, here it is given the velocity differ by factor 2. Mind it, they are not saying about the K max, they are telling about the velocity. So we need to find the relationship between K max and velocity. The K relation between is basically Ke, we know half mv square. Fine. Now this half m is constant, this is not changing. What the changing factor is this velocity. So what we can write it as Ke1 by Ke2. The velocity differ by factor 2. See, the 2 cases differ by factor 2. So what I can write, in first case the velocity, if it is 2v, then the second case it will be v whole square. I hope it's clear, because in this question it was said that the velocity differ by factor 2. So in first case, if we consider the velocity as 2b, then it will be the just half. In the second case, there is 2b by v. So it's quite simple, I hope. So that's Ke1 by Ke2, what I can write it as 4. And now we can use it directly in this 2 equation. Okay, now if we divide 1 by 2, what we can obtain, Here is 4 equal to, you can say, write this part, Hc by 350 into 10 raised to the power minus 9 minus 5. We need to find is 5. Hc by 540 into 10 raised to the power minus 9 minus 5. Now it's simple, it's just a calculation based approach, nothing more, like nothing more conceptual left here. So let us calculate it, and before calculating this, we need to put the value of Hc. The value H is there is a Planck constant, and its value is 6.6 into 10 to the power minus 34 meter square kg per second. And the value of C, that is speed of light, as we know, 3 into 10 to the power 8 meter per second. On putting everything, putting these two values there, and after calculating, we'll get phi close to your 1.8, we can say 1.83, or that is close to your 1.8. That is option number, let me check the option number D. Option number D is the correct one. I hope it's the discussion is entirely clear to you. So concluding the entire topic, I have taught you about, we can say, the photoelectric emission, also related important terms, and this Einstein equation, and I have illustrated with an example, a previous year JEE Mains example stating this question. I hope it's entirely clear to you, and have a good day. Thank you, student.